students, welcome to a new session for the chapter Haloalkanes and Haloarenes. From the previous few sessions, we have been seeing preparations of haloalkanes and we have been doing a preparation of haloalkanes from alcohols. In that we have seen Gru's process where we prepared haloalkanes from alcohols using Lucas reagent. Then we have done the preparations of haloalkanes using alcohols. What was the reagent? PCl₅ gaseous and solid form, and then we have seen with PCl₃. Today it is going to be the last preparation method of haloalkanes from alcohols. Okay, now the last reagent we are going to use to prepare haloalkanes from alcohols is going to be SOCl₂. So we'll take alcohol and treat it with SOCl₂. Okay, treat it with SOCl₂. Then what we will get? We will be getting RCl plus sulfur dioxide plus HCl gas. Okay, so this will be our products when I treat alcohol with SOCl₂. SOCl₂, if you want to know the name, it is your thionyl chloride. It is your thionyl chloride, and this method is considered to be the most beneficial method for the preparation or the most efficient method for the preparation of haloalkanes. So you can write it as most efficient method for the preparation of haloalkanes. It is considered to be the most efficient method for the preparation of haloalkanes. Now, in science we should not accept anything without knowing the reason. Now, if we say it is the most beneficial method, or if we say if it is the most efficient method for the preparation of haloalkanes, we should know the reason. If you see the byproducts of this reaction, our main product is RCl. If you see the byproducts of this reaction, both of them are gases. Okay, sulfur dioxide is a gas and even HCl is released as a gas. As both of them are gases, okay, they move out. Okay, they move out easily. Okay, they move out from the reaction mixture easily. Okay, for example, if you are taking, there is a big container in which this reaction is happening. In that reaction, obviously the gases generated are SO2 and HCl. As both of them are gases, they easily leave the reaction mixture very easily. Because our main motto is RCl, we need RCl from the reaction. So when both the gases leave the container easily, it is okay. What is left in the container? Only RCl. Okay, so you can happily take it out and use it for the required purpose. Now, if you go for the other processes, the water byproducts which are getting produced, okay, they might not be gases, or if they are gases, they might not easily leave the reaction mixture. So in this case, you don't have the problem. Both of them are gases and they easily leave the reaction mixture, leaving out your RCl in the reaction mixture. So you know the process is very simple to get the haloalkane. Now, if you see the mechanism of the reaction, you will easily understand like what kind of haloalkane is formed. Okay, what is the stereochemistry? Is it inversion or it is retention? All that we will see. Now, here if you see the reaction, now I will make you people understand what is the mechanism of the reaction. This reaction is very famously called as Darzen's reaction. Okay, very famous. It's a named reaction. As long as it is a named reaction, all the named reactions are very, very, very important. If you see the mechanism, as I told you before, alcohols, okay, oxygen has 2 lone pairs of electrons, so it will react with my thionyl chloride SOCl₂. Okay, now if you see in PCl₃ and PCl₅, I was clearly explaining you why is phosphorus more interested on the lone pairs of oxygen. In the same way, here also we'll try to focus why is sulfur more interested on the lone pair of oxygen. Okay, now if you see both the chlorine atoms and the oxygen atom which surround sulfur in this compound, they are all highly electronegative. Chlorine and oxygen are very highly electronegative, so they will be pulling the shared pair of electrons more towards their side. So ultimately, sulfur will feel that okay, the electrons are not with me; they are always with the more electronegative atoms, oxygen and 2 chlorine atoms. So it will try to pull electrons from a lone pair of electrons from oxygen. Okay, it will try to pull the lone pair of electrons from oxygen. Now, what will happen? Oxygen, as it loses its lone pair of electrons, will get a positive charge. Other lone pair of electrons are still there. Now it is hydrogen. Now then, when sulfur has taken lone pair of electrons from oxygen, chlorine will be like, okay, you have taken from oxygen. Now I will happily leave with my electrons. Okay, I will happily leave with my electrons. So here, from this molecule, Cl- is lost. Okay, where it is going, we will see slowly. Okay, now if you see, what do you get here? SOCl. Now here, as I always keep telling you, oxygen is not stable with positive charge. So it will try to take the shared pair of electrons either from here. If you think, I always told you that after knowing the products only we'll predict the mechanism. Now if you see the products, you can clearly see SO2 gas here. So definitely oxygen did not pull electrons from this bond. You can see HCl formation, so might be oxygen has pulled electrons from this bond. So hydrogen will go as H plus and react with this Cl minus, and HCl gas is being evolved. So the possibility of that is more based on the products formed in this reaction. So oxygen will try to pull this shared pair of electrons towards itself. Now what do you get here? Oxygen will not have any positive charge now because it has taken the shared pair of electrons from hydrogen. Now oxygen will have its two lone pairs of electrons. It is my SOCl. Now Cl minus from here, hydrogen as H plus from here. Together they will leave the reaction mixture as HCl gas, which I already told here. HCl gas will be released from the reaction mixture. Now again sulfur will be like, oxygen now has two lone pair of electrons, so let me pull the electrons again, and here the sulfur will try to pull the lone pair of electrons, resulting in the formation of a double bond here. Now if you see here what is formed here, oxygen has lost its lone pair again because sulfur has pulled it. So here you can see the formation of double bond. Oxygen again getting its positive charge, the other lone pair is still there, and Cl here. Now this is very important step. Try to observe the step. As I always keep telling you, oxygen is never stable with its positive charge. It's never stable with its positive charge. So it will try to pull the electrons from this bond. In the meanwhile, what chlorine will do is, it will be like sulfur is mostly messing with oxygen only now. Sulfur is more interested with messing with oxygen, and it has already formed four bonds with oxygen. So chlorine will go and attack on this R bond. So chlorine is like, sulfur is no longer interested in me, and it is more with oxygen. It has formed enough bonds with oxygen. So chlorine along with its shared pair of electrons leaves sulfur and attacks your R group here. Now oxygen very happily will pull the shared pair of electrons towards itself. Now if you see here, the nucleophile is attacking within the molecule. So the nucleophile is attacking, Cl minus is the nucleophile. The nucleophile is attacking within the molecule. Now whenever the nucleophile is attacking within the molecule, I explained you in the reaction mechanism when I was teaching you ROH plus PCl₅ gas gives RCl plus POCl3 plus HCl. There I clearly told you, whenever the nucleophilic attack is happening within the molecule, it is your SNI, intramolecular nucleophilic substitution reaction. It will be your intramolecular nucleophilic substitution reaction. Now what do you see here? RCl is formed. Now whenever the attack is intramolecular, Cl minus will come and take the same place as the bond, as the group that is leaving. Oxygen is leaving from R, so Cl minus will come and occupy the same place as oxygen was occupying. So whenever the mechanism is SNI, intramolecular nucleophilic substitution reaction, the product will always have the retented configuration. So the configuration is retained. So I will see the retention in my product, plus which gas? Sulfur with two oxygens will be liberated as SO2 gas. So SO2 gas is liberated at the end of the reaction. In between the reaction, I showed you the release of HCl gas, and my final product is my haloalkane with a clear retention of configuration. Now this is how this reaction goes when you take thionyl chloride SOCl₂ as your reagent. I told you it is very efficient reaction because both the byproducts which are produced in this reaction leave the reaction the mixture very easily. So getting our main product is very easy. If you want SO2 and HCl gases for any further reaction, if you want to retain them and use it for any other reaction, you can condense them and use it further. Now, as long as it is like this, it is very simple. But in the exam, if you see, they give the same reaction sometimes in the presence of pyridine. Now, if they don't give, anything on the aroma, or if they don't mention about pyridine, you will get RCl plus SO2 plus HCl with a retention of configuration. Now, in the exam, if they have used pyridine, it doesn't mean that your products will change. The products will still remain the same. But the difference will be there with the configuration. the difference will be there with respect to the configuration. Now, why is the configuration getting inverted? What happens if pyridine is there in the reaction? We can only clearly understand if we see the mechanism of that reaction. Hopefully this mechanism is clear. In the absence of pyridine, you can see the retention of configuration. Clear? Now, if pyridine is there in the reaction, what happens? Why are we getting an inverted product? Let us see that now. Now let us see the reaction in the presence of pyridine. Now, if we before knowing the mechanism, little bit we'll understand the structure of pyridine. Pyridine is a heterocyclic compound. Okay, its formula is C5H5N, and it is it has a ring-like structure. Okay, in which you have nitrogen. Okay, so C5H5N is the pyridine structure. You should know it because you have to understand the mechanism here. Now, if you see the mechanism here, okay, no, most of the steps are similar like before. Only there will be minor changes which I will be explaining. Okay, alcohol, oxygen with its lone pair of electrons, SOCl₂. Okay, this story is same as before. Sulfur will try to take electrons from oxygen. Now, oxygen will get a positive charge here. Okay, as oxygen lone pair gets attacked on sulfur, chlorine leaves with its shared pair of electrons, and Cl- is released from here. Okay, so we can write here Cl- goes from this compound. Now what is left for me here? SOCl. Okay, this is same as before. Now what happens? Even the next step is like before. Only oxygen will try to take the shared pair of electrons from hydrogen. Now okay, let me write the product, then I'll explain you one thing. So oxygen will not have any positive charge because it has taken the shared pair of electrons which it had with hydrogen. Now I got this. Now if you see here, Cl- is released from here, H+ is released from here. Both of them they'll react with pyridine because I'm using pyridine in this reaction. Both of them will react with pyridine, forming okay. H+ and Cl- will come from here and they react with pyridine, forming here pyridinium chloride. Now what does pyridinium chloride do in this reaction? We will see. Okay, but here what you need to remember till now, see the process is same as before. Okay, in the previous case when there was when pyridine was not there in the reaction also, the similar thing was happening. But what is the difference here? The HCl which has been released in this step, it will go and react with pyridine. Previously it was released as a gas. Okay, now it will react with pyridine, okay, and form pyridinium chloride. What will this pyridinium chloride do? We will see. Okay, now okay, what will be the next step in this reaction? If you see the next step in this reaction, okay, now sulfur will become greedy. Okay, it will be like, okay, let me take one more let me take lone pair from oxygen, and it will try to pull the lone pair from oxygen here. Okay, now what will happen? Oxygen has lost its lone pair, so here you will get positive charge. Here there will be a double bond, S double bond O. Okay, this is what I get. Okay, this is what I get. Now whatever we are going to see here, this is going to be a very crucial step. Okay, whatever we are going to see here is very crucial step. Okay, now let me I'll explain you the mechanism in this way. Then we will try. Or let me do one thing. Okay, let me take a compound. Okay, let me take a compound which has chiral carbon so that you understand these things better. Okay, let me take a compound which has a chiral carbon. That is better. Okay, then you will have lot more clarity of how is this process happening. So I'll just give me a second. I'll just change it to a, because if I take like normal R and do it, I cannot show you people inversion properly in this reaction, because in this reaction inversion happens. So let me take a chiral alcohol only and show you the reaction so that you people can understand the inversion better. Okay, so that you people can understand the inversion better. Yeah. Now it will be easy for you to understand. Okay, so obviously you have a chiral center, you have a chiral alcohol. So I am proceeding with the chiral alcohol so that in the last step, when I talk about retention and inversion, it will be very easy for you to understand. Now exactly what happens, let us try to understand. Oxygen is definitely not stable with its positive charge, so it will try to take electrons from here. In the meanwhile, what will happen is this Cl- is there, right? In the pyridinium chloride, this Cl- is there. This Cl- from pyridinium chloride will act act now, and it will try to attack this carbon, because now Cl minus will be it is electron rich. Now because oxygen is with positive charge, is with positive charge, this oxygen will try to pull electrons from this bond. So at that time what will happen, Cl minus, because it is a nucleophile, it sees an electron deficient site at carbon. It sees carbon as an electron deficient site, and quickly this Cl minus will try to attack from the back side. Okay, this Cl minus will try to attack from the back side. So it is very much clearly understood this is going to be your SN2 mechanism. It is going to be a SN2 mechanism. Now if you see here what exactly will happen, I'll make you understand. Now now when Cl minus attacks here, okay, and this obviously this oxygen was also waiting for to take this to take these electrons towards itself. Now, if you want to understand the inversion process very properly here, I will show you how is the bond made and how is the bond breaking taking place here. So you people clearly understood this is going to be an SN2 reaction because nucleophile is attacking from the backside. Now what will happen? Now the bond, see, Cl minus will try and form a new bond with the carbon here. Okay, will try and form new bond with the carbon here. Now, as you people can see here, here there is carbon oxygen bond. If Cl minus is coming and attacking on the same side, and if Cl minus is occupying the same place as oxygen was occupying, then it would have been retention. So Cl minus will occupy the place opposite to that of the carbon oxygen bond. So it will be my inverted configuration. Now what will happen? Okay, so as you people know, inversion of configuration takes place. Here. Okay, so you have your what here? Okay, because it gets inverted. Okay, chloride has attacked from this side, so CH3 will go to that side. Okay, hydrogen is there here. Okay, this bond has become this bond is about to break here. Now oxygen will not have any charge because it has taken the electrons from this side. Okay, and this Cl bond will become weak. Okay, new carbon Cl bond is getting formed, and the sulfur chlorine bond the bond is getting broken. So you can see a bond making and you can see a bond breaking here. Now from here what will form here? Cl minus has attacked from here, so you will get CPH CH3H, and this will be your inversion. And what is this? This will be your inversion plus SO2. Okay, plus SO2. Clear? Plus SO2 gas, as I mentioned before, this will be your SO2 gas. Now this Cl, this Cl has been detached from sulfur. This Cl has been detached from sulfur. It will go to the hydrogen. Okay, forming HCl gas, and because from this pyridinium chloride, Cl minus has attacked from backside. So this Cl minus has been used here. Now because this Cl got separated, bond making, and this Cl which was attached to sulfur got separated, that Cl will go and grab this hydrogen, forming my HCl gas. And at the end of the reaction, pyridinium will be C5H5 and pyridine. Okay, at the end of the reaction, your pyridine is what? Retained. Okay, at the end of the reaction, your pyridine is retained. You got the product. Okay, you got the haloalkane with the inversion configuration. Along with that, SO2 gas has been released and HCl gas also has been released. Now in this reaction, clearly you can see SN2 mechanism is involved, and you can see a clear inversion of configuration. Here. Now when pyridine was not present, it was a retention configuration, and the mechanism was SNI mechanism. Now when pyridine is involved, now the reaction has gone through SN2 mechanism, and my product is an inverted product. So this is what you need to take care in the examination point of view. When pyridine is not there, the mechanism is SNI and there is retention of configuration. And when pyridine is used, there is a SN2 mechanism and there is inversion of configuration. See, normally, products are same. That every child can answer. Okay, you will get more grip on the concepts, and you can answer diverse questions on Darzens reaction only when you know only when you know the stereochemistry of the reaction. So you should know the stereochemistry of the reaction in the presence and absence of pyridine. So that is clearly understood through the mechanism. Now let me take an example to make you understand the stereochemistry better. Okay, if it is without pyridine, how will the product be? And if it is with pyridine, how will the product be? So for that, we'll see an example along with the stereochemistry. Hope you understood the mechanism. I told you the mechanism so that you understand the things better. Okay, from see till here it is same. Here the difference comes from this step, because Cl minus from pyridinium chloride will attack from the back side. Okay, that will create the inversion of configuration here. So this step is the deciding step. And where is the Cl minus coming from? Pyridinium chloride. I hope you understood the role of pyridine here. Pyridine becomes pyridinium chloride, and when this the Cl minus here sees, okay, the Cl minus here sees the electron deficient carbon, it will come and attack here, giving the inverted configuration. Now let's see an example to understand stereochemistry better. Now let us take an example to understand the stereochemistry better. Okay. Now if you see this is a this is an alcohol. This is an alcohol with a chiral center. Okay, this is an alcohol with a chiral center. Carbon on one side has hydrogen. Okay, when you have I think you have studied all this in your stereochemistry part in your grade 11. I'll make this. Okay. When it is hydrogen is present behind the plane. Okay, OH is present. Okay, in front of the plane, and COOH, both CH2COOH and COOH, both these groups are present on the plane. Okay, we have four different groups on four different groups. So I have a chiral carbon. So this is my chiral alcohol. I have taken this example so that you understand the stereochemistry part better, because it has chirality. So whenever there is no chiral carbon, there is no point of inversion and retention. Now when I have chiral carbon, I can explain you retention and inversion in a better way. Now here the SOCl₂ is in the absence of pyridine. So what mechanism do you see here? SNI mechanism. And whenever the mechanism is SNI, there will be retention of configuration. So the nucleophile Cl minus will go and attack. Okay, the nucleophile Cl minus will go and attack and take the place of OH. Okay, and take the place of OH in the same direction. So if you see here, this will be my chiral carbon OH. Okay, this will be CH2COOH, and this is OH was there coming out of the plane of the paper towards us. So Cl will take the same side, and hydrogen is here. So what do you see here? You can clearly see the retention of configuration here, plus SO2 gas and HCl gases. Both the gases are out. Now if you see in the presence of pyridine, there will be an inversion of configuration. How should I show the inversion of configuration here? COOH. Okay, OH. Now if you see here, Cl minus will come as a nucleophile. If it takes the same plane as OH as taken, then it will be reduction. It will not take. Okay, it forms an inverted product, so it will take the orientation opposite to the side of OH group. So if OH group, so if OH group is present coming outside the plane of paper, the Cl minus will be attacking behind the plane. So the Cl minus will be attacking from behind the plane. Okay, and here now your H. Okay, there is inversion of configuration. Okay, Cl minus will attack from the from the plane which is opposite to OH, which is this is in front of the plane. So Cl minus will attack behind the plane. So there is inversion of configuration, and hydrogen will come in front of the plane. Okay, Cl minus will go behind the plane. H will come in front of the plane. So you can clearly see inversion of configuration here, along with the release of SO2 gas and HCl gas. Okay, so this is how you can easily understand the stereochemistry. Mechanism is for your understanding of why is this happening. In exam, you should be able to identify which is a retention product and which is an inversion product, under what reaction conditions which product is produced. And you also have to always remember Darzens reaction is the most efficient method of preparation of haloalkanes. With this, we come to the end of the preparation of haloalkanes from alcohols. We started the preparation. First we have prepared haloalkanes from alkanes, then we have prepared haloalkanes from alkenes, then we have prepared haloalkanes from alcohols, and in the next session we will be doing 3 to 4 important named reactions for the production of haloalkanes. With that would be the last session for the preparations of haloalkanes. Then we would be moving forward with the preparation of haloarenes. Clear? So in the next session, I'll see you with some very important named reactions, very interesting named reactions. Okay, and for your happiness, they won't have so many mechanisms involved in them. Clear? Okay, hope you loved this, loved the explanation today of Darzen's reaction with SOCl₂ with pyridine and SOCl₂ without pyridine, and what is the difference in the configuration, why is the configuration changing when I have put pyridine in the reaction. Hope you understood everything and you loved the session. Okay, I'll see you in the next session with some named reaction. Till then, bye.